January 1944, above northern France. The sky is thin and savage at 25,000 feet. Frost crusts on gun ports. Contrails stretch like white veins across the blue. Below, a German FW-1908 claws upward, engine howling in protest. The Luftwaffe pilot has seen his prey, four silver hulks lumbering toward the channel. American P-47 Thunderbolts, broad-shouldered, glinting in the sun. Too big, too heavy, too slow, he thinks. Easy kills. He dives to strike. But as his prop bites the thin air, something unexpected happens. The lead P-47 pitches its nose skyward and rockets upward. Then another. Then all of them. Their wings shimmer from the heat pouring out of exhaust ports beneath their tails. Within seconds, the hunter finds himself hunted. The Thunderbolt screams past him, climbing higher, faster, as if fueled by something unnatural. The radio crackles with panicked German voices. Impossible, they're climbing. Somewhere below the clouds, in a maintenance tent stained with oil and sweat, a mechanic wipes his hands on a rag, proud of a crude but brilliant adjustment. The line between science and madness, it seems, can be measured in inches of turbine metal. To understand the miracle of that climb, we have to return to a very different sky, one clouded not by exhaust but by doubt. In 1939, the United States Army Air Corps knew it lagged behind. Across the Atlantic, Germany's fighters were already legends. The Bf-109, the FW-190, sleek, fast, perfectly tuned for the Blitzkrieg's lightning wars. America's aircraft, by contrast, looked like relics of another decade, underpowered, short-ranged, and gasping for air above 20,000 feet. Inside the offices of the Republic Aviation Corporation on Long Island, New York, Alexander Kartveli, the company's chief designer, wrestled with impossibilities. The Air Corps wanted a high-altitude interceptor with heavy guns, long range, and rugged construction. Practically every engineer agreed it couldn't be done with their existing tools. Pistons lost power at altitude, compressors added dangerous weight, and airframes large enough to carry those systems slowed down until they were sitting ducks. Kartveli's answer was audacious. He designed an aircraft around a positively enormous engine, the Pratt & Whitney R2800 Double Wasp, an 18-cylinder powerhouse producing more than 2,000 horsepower. But raw power alone wasn't enough. At high altitude, where oxygen thins, even the R2800 suffocated. What it needed was a turbo supercharger, a machine that would use exhaust gases to spin a turbine, compress incoming air, and deliver it back to the engine with the same pressure it would feel at sea level. It was technology first explored by Dr. Sanford A. Moss, an American engineer whose pre-war experiments at General Electric had shown how exhaust energy could be recycled into thrust and compression. His early prototypes had powered test beds like the B-17 Flying Fortress, but never a single-engine fighter. Installing Moss's creation into Kartveli's design seemed nearly impossible. The turbo supercharger was bulky, fragile, and demanded yards of precise ducting to channel exhaust gases without cooking the airframe alive. Where could it possibly fit? Kartveli's team found a bold answer: in the tail. While rival fighters carried their superchargers crammed tight behind the engine, Kartveli sent the exhaust through long pipes twisting under the belly to a great turbine mounted behind the cockpit. The idea was radical. It distributed weight evenly, cleared room near the nose for armament and fuel, and promised unmatched performance in thin air. But it also meant an aircraft both huge and complex. The P-47 prototype, named XP-47B, rolled out in 1940 weighing nearly twice as much as any Allied single-engine fighter. Pilots called it a jug, short for juggernaut. When Kartveli's creation first roared down the runway, its immense propeller sent a storm of dust across Republic's field. Test pilot Lowell Bales throttled up, and the crowd watched the jug lift gracefully into the gray afternoon, faster than anyone expected. Yet early trials revealed crippling flaws. The long turbo pipes overheated, ducting leaked pressure, and the complex routing demanded a mechanic's near-religious precision. The airplane's promise was clear, but so were its growing pains. Meanwhile, Europe fell deeper into chaos. France collapsed. Britain fought alone. In the Pacific, Pearl Harbor pulled America into full war. Factories roared to life on both coasts. The Air Force wanted the P-47 not someday, but now, and it needed to work, no matter what. What happened next was less the triumph of theory and more the hard-won wisdom of thousands of mechanics facing the bitter cold of English airfields. Production Thunderbolts arrived at bases under a shroud of secrecy, their tail turbo systems still temperamental. The pipes warped in temperature swings, the wastegate valves stuck, the delicate turbine blades cracked from vibration. Every squadron soon had its own solutions. Some mechanics rerouted exhaust flow using repurposed tank parts. Others fabricated clumsy but brilliant sheet metal shrouds to channel airflow more efficiently. It wasn't factory engineering, it was trench ingenuity. And one of those grease-blackened minds soon discovered a subtle alteration that would change the Thunderbolt's destiny. By adjusting the pressure control linkage that governed wastegate response, the turbo could surge into higher output more aggressively, giving quicker climb at the risk of overspeed. To headquarters, it looked reckless. To pilots fighting for survival over occupied France, it felt like salvation. The altitude war was about to tilt. The factories back in America were already racing to refine Cartveli's design, but frontline adaptation was defining the machine's legend day by day. Back in the States, far from combat, a different battle was raging, one fought in drafting rooms and wind tunnels rather than in the skies. Republic Aviation's engineers were trying to tame the monster they had unleashed. The P-47s turbo supercharger gave the Thunderbolt breathtaking theoretical performance, but every small variable affected it. Temperature gradients, altitude transitions, even how tightly a mechanic sealed a joint. To many outsiders, it looked like over-engineering gone mad. The Luftwaffe fielded lighter, simpler fighters. The WWII, the latest Bf-109G, each built to be field-repaired in barn hangars by mechanics armed with little more than wrenches. The Thunderbolt, by contrast, was a flying refinery of bronze ducts, regulators, and intercoolers. It bore more resemblance to a power plant than to a plane. Yet therein lay its peculiar genius. Its complexity gave it potential. In 1942 and 1943, the Army Air Forces pressed Republic and General Electric to standardize turbo construction. The companies improved metallurgy, designed better intercoolers, and refined the turbine's vane geometry so that the unit could handle sustained high-temperature loads. Still, these upgrades had to survive transatlantic travel, assembly at British bases, and the rough improvisations of combat operations. Enter the mechanics world, tin huts, mud, and improvisation bordering on artistry. One of these was T/Sergeant Harold "Pops" Carr, who served in the 56th Fighter Group stationed in England. Like many mechanics, Carr was part scientist, part gambler. He noticed that the turbo's pressure control system lagged during quick throttle movements, wasting precious seconds in dogfights where altitude meant life or death. Experimenting with linkage lengths, spring tension, and wastegate actuation, Carr found that tightening a specific control rod shortened response time dramatically. It wasn't an official engineering order, it was a field hack. But the results were undeniable. Pilots who flew Carr's aircraft returned with astonishment. Their jugs climbed hundreds of feet per minute faster at altitude, and the turbos responded crisply instead of sluggishly. News spread through the group and out to sister squadrons. What Carr had done, others repeated under different names and variations. Tech orders never formally described it, but every mechanic now kept a mental note about tweaking the turbo linkage. The transformation was more psychological than mechanical. Crews began to trust the P-47 not as an overweight brute, but as a living, breathing machine they could understand and improve. Once regarded as a clumsy stepchild of high-tech excess, the jug became the maintenance man's masterpiece, a canvas of rivets and hoses on which human ingenuity could paint. Meanwhile, leadership took notice. General William E. Kepner, overseeing fighter operations in the 8th Air Force, recognized that these field modifications were producing measurable combat improvements. He ordered test flights comparing standard and adjusted aircraft. The results verified what the mechanics had known for weeks. With the fine-tuned wastegate and slightly altered turbine shroud geometry, climb rates increased and turbo failures decreased. By the summer of 1943, P-47 units over Europe were claiming aerial victories at an accelerating pace. What began as an experiment in metal and heat had turned into a doctrine of adaptability. The lessons spread outward, to depots, training manuals, and eventually to Republic's own engineers, who incorporated some of the field insights into later production models. In a sense, America's sprawling war industry and its frontline improvisers were now cooperating in an unspoken partnership. Engineers pushed theoretical limits. Soldiers made the theories practical. That partnership reflected something deeply American: mass production fused with individual initiative, a blend the rigid German system rarely tolerated. Yet the price of that innovation was steep. The early months of the P-47s European service were filled with accidents, engine fires, and bewildered young pilots trying to master a machine whose optimal handling charts could fill a textbook. But each failure yielded data. Each burned turbo housing led to smarter ducting. Slowly, a pattern emerged. The combination of the R28's brute strength and the turbo supercharger's altitude efficiency made the P-47 unbeatable above 25,000 feet. By late 1943, the Luftwaffe's pilots began reporting something unnerving. American jugs were climbing vertically past interception altitude, even with full bomb loads. Their engines didn't fade with altitude, they seemed to strengthen. The balance of air power was shifting, not through new weapons, but through the untidy art of human problem-solving. And yet the story of the P-47's rise isn't just a mechanical chronicle. It's a mosaic of perspectives, each revealing how one innovation reshaped lives, tactics, and even morality within the whirlpool of total war. In every hangar, every flight line, the P-47's transformation told a different story. It wasn't one innovation, it was 1,000 small acts of observation, judgment, and courage stitched together by necessity. When people later talked about the Thunderbolt's secret weapon, they rarely meant the turbocharger alone. They meant the spirit behind it. The men who worked on those aircraft lived in a world of fumes and noise. By dawn, their fingertips were black with oil. By midnight, they were frostbitten from the icy English winters. They slept in makeshift huts just yards from the main runway, roused by the growl of propellers every morning. The Luftwaffe's survival often depended on its pilots, aces adorned with medals and fame, while America's successes often began with unnamed technicians like Popscar and his peers. They didn't have the luxury of textbooks or theory. They learned through scars, burned knuckles, shattered turbine blades, near misses with exploding compressors. They observed tiny nuances: the color of flame tongues at exhaust ports, the vibrations at mid-altitude climbs, the subtle pitch of the R28 when transitioning into turbo mode. Pilots trusted their mechanics completely. Before takeoff, they'd meet eyes across the tarmac, a silent agreement. If the machine failed, one of them wouldn't return. Mechanics carried that weight like ballast. It drove them to chase perfection not out of pride, but survival. To them, the insane turbo hack wasn't daring, it was mercy. When the adjusted turbo linkages began rolling through groups in late 1943, squadron leaders noticed a sudden shift in combat rhythm. Before, the P-47's power came alive only after a long build-up. By the time the turbo spooled to pressure, the opportunity was gone. With the new setting, thrust arrived almost instantly, and the aircraft could convert energy into vertical maneuvers that surprised even seasoned Luftwaffe pilots. In dogfights over France and the Netherlands, the big American fighter began rewriting air doctrine. Where Allied pilots once avoided close-turning engagements, P-47s now played them deliberately, climbing upward in winding spirals where their turbos thrived on thin air. German FW-190s, optimized for low-altitude power, started to lose steam beyond 20,000 feet. Their tactic, zoom, strike, dive away, no longer guaranteed escape. The Thunderbolt's new advantage changed escort strategy, too. Bombers flying deep into Germany finally had dedicated protection capable of meeting enemy fighters at their chosen altitudes. What had been a vulnerability became supremacy. Behind every new statistic, a higher survival rate for bomber crews, a falling intercept success for the Luftwaffe, lay a handful of turns with a mechanic's wrench. It is easy to speak of the turbo as one device, but the Thunderbolt's strength lay in the harmony of its systems. The General Electric B-Series turbocharger sat far aft, connected by a network of exhaust pipes nearly 12 feet long. These carried gases into a turbine wheel spinning at over 20,000 revolutions per minute. A shaft from that turbine turned a compressor wheel that forced air through an intercooler, cooling it before delivery to the mechanical supercharger mounted on the engine itself. The result was a two-stage, two-speed form of breathing. Rarefied air, compressed twice and cooled once, fed the R-20 cylinders with dense, explosive oxygen even at 30,000 feet. The combination produced steady manifold pressure, vital power consistency at altitude. Yet this same system made the jug seem like a mechanical puzzle box. Mechanics weren't just fixing airplanes. They were tuning resonances, balancing temperatures like metallurgical therapists. The hack that optimized wastegate responsiveness only worked because the rest of the design could tolerate the increased strain. It was a miracle the airframe absorbed it at all. In essence, every P-47 carried a compact industrial revolution inside its skin, a turbine plant in miniature. That audacity captured something essential about American engineering during World War II. Huge, redundant, complex, but capable of performance no one else dared to attempt. Above the chaos of the flight line sat a structure of command that could easily have smothered creativity. The U.S. Army Air Forces, mindful of regulations, maintained strict engineering protocols. Modifying a multi-million-dollar aircraft without authorization bordered on insubordination. Yet within operations groups like the 56th and 78th Fighter Groups, leaders recognized that improvisation was keeping men alive. Colonel Hubert Hub Zemke, commander of the 56th, became one of the first to defend his mechanics' right to experiment. "If the boy can make it climb, let him," he once said when questioned about the linkage adjustments. His stance created a culture where innovation trickled upward instead of downward. The official paperwork lagged months behind. By the time new technical bulletins sanctioned higher allowable turbo speeds, frontline squadrons had already been flying that way for weeks. Leadership's greatest achievement was to allow the unofficial to become the indispensable, to trust those who understood not the theory of war, but its temperature and smell. That chain of trust, connecting grease-streaked hands to brass-button decisions, created a style of warfare built on elasticity rather than dogma. It was a network, not a hierarchy, and in that network, genius could surface anywhere. And as the turbo's hiss and spool reached its war-ready crescendo, a mirror image was forming on the opposite side of the channel. The Luftwaffe, watching its altitude dominance erode, began its own desperate search for a countermeasure. If the Thunderbolt's triumph was an anthem to improvisation, its echoes were heard just as loudly inside enemy command rooms. German engineers studied American wrecks whenever possible, trying to understand why this massive, radial-engined fighter climbed like a falcon. What they found astonished them. Captured reports from the Luftwaffe's technical office in 1944 spoke of an unusually efficient turbo apparatus positioned aft. The placement baffled them. German designers had long experimented with exhaust-driven superchargers, but their limited high-temperature metals and manufacturing precision made those attempts dangerous and expensive. The Americans, with abundant nickel and chromium alloys, simply outproduced those constraints. German pilots noticed the consequences first. At altitude, their acceleration resembles that of twin-engined fighters, wrote one officer after surviving an engagement over the Ruhr. Another report noted, "They appear invulnerable to steep dive pursuit. They climb away at full throttle beyond 20,000 feet." The Luftwaffe responded predictably, with technology races of its own. BMW and Junkers engineers worked frantically on advanced turbo-boosted piston engines and, later, jet propulsion. But the American turbocharger's combination of materials science and field reliability remained beyond quick imitation. The P-47's very existence forced German planners to accelerate pursuit of the Me-262 jet, a desperate leapfrog attempt that carried its own production chaos. So while the Allies gained incremental power through clever mechanical adaptation, the Axis sought salvation in radical reinvention. It was the difference between evolution and revolution, and wartime history shows which survives more reliably. Behind every squadron in England, there stood the relentless thrum of American factories. The P-47 program consumed vast quantities of copper tubing, heat-resistant steel, and precision-machined turbine blades. General Electric plants in Lynn, Massachusetts, and Schenectady produced turbos almost as fast as Republic could bolt them into fuselages. American mechanics joked that each month's batch came with improvements nobody told us about. Continuous feedback between field maintenance crews and engineers ensured that manufacturing responded pragmatically. Pipes thickened where cracks appeared, access panels rearranged for field convenience. That adaptive production flow became part of the weapon. Where Germany's narrow resource base restricted experimentation, America's allowed iteration. A clever mechanic in England could draw a diagram of a modification. Within 6 weeks, a factory revision might incorporate it nationally. It wasn't efficiency in the bureaucratic sense. It was flexibility at industrial scale. The turbo hack succeeded because the system around it allowed learning to multiply. History often interprets technological triumph as linear genius, but here it looked more like a conversation between draftsmen, laborers, test pilots, and exhausted men bent over midnight workbenches with cigarettes burning low. There's an uncomfortable grandeur in mechanical success during wartime. Every solved equation, every polished blade was designed to prolong life on one side and erase it on the other. The P-47's turbo advantage didn't merely improve performance. It pushed the air war into new altitudes where interceptors struggled, forcing defensive shifts that cost thousands of lives. Some of the same mechanics who refined the turbo supercharger would later express pride mixed with melancholy. Their skill, so essential to safety and progress in peacetime, had been applied to perfect the means of killing. One post-war diary entry from an anonymous Republic technician reads, "We built engines that breathed where men could not. It is beautiful, but it is also terrible. Yet few of them saw alternatives." Total war erased distinctions between creation and destruction. To these builders and maintainers, doing their job well equaled survival for brothers, sons, and friends overseas. In that moral dissonance, the elegance of turbines serving the brutality of combat, lies the haunting poetry of the P-47's story. If one were to choose a single aircraft to personify American wartime identity, the Thunderbolt stands out. It wasn't sleek. Early critics called it overfed, even grotesque. But its brawn, reliability, and capacity to be improved mirrored America itself. Inexperienced at first, inventive under stress, overwhelming in endurance. Each field innovation, every improvised panel, every insane turbo tweak, was a miniature reenactment of the national arc. The country had entered the war clumsy and uncertain, and by 1944 it had mastered both precision and improvisation in equal measure. The Thunderbolt became an airborne metaphor for that duality. Heavy but agile, sophisticated yet approachable, scientific yet homespun. When the aircraft reached its peak configuration, it could escort bombers deep into the Reich, climb higher than its opponents, and dive faster than any piston fighter ever built. The power plant that once seemed too complicated was now the reason for its unmatched versatility. And so the insane hack, born from a mechanic's intuition and a line engineer's willingness to trust him, became inseparable from the aircraft's identity. It exemplified victory by problem solving, not by perfection, but by relentless adjustment. The war in the air continued to escalate. Over France and the Rhineland, the Thunderbolt's turbos wailed like sirens at sunrise, heralding the raids of 1944. Luftwaffe controllers charted altitude patterns and realized, too late, that no existing piston fighter could match the Americans above 25,000 feet. The stage was set for the showdown that would finally prove the full power of the turbocharged Jug, a single day when the balance tipped irreversibly toward Allied skies. Dawn, March 8, 1944, somewhere over the Eifel Mountains, Western Germany. Flight Lieutenant Francis Gabby Gabreski pulls his P-47D into a steep climb so aggressive that his stomach folds against his harness. His canopy frosts with sudden chill. Fuel lines groan. The altimeter winds past 20,000 and keeps spinning. Below him, the bomber stream, hundreds of B-17s droning toward targets near Castle, glitters like a chain of silver beads stretching to the horizon. Above him swirls a different glint, enemy fighters, closing fast. Radio chatter bursts against the oxygen hiss. Bandits 12 o'clock high. Multiple 190s. It's the kind of moment that once spelled disaster for the 8th Air Force. But this time, Gabreski's group doesn't dive for safety. Instead, they rise to meet the attack head-on. The squadron's machines, each tuned by the same field modifications polished through months of practice, respond instantly. Turbo housings shriek as exhaust gases spin turbines beyond design spec. Wastegates snap open, pressure surges, and the Thunderbolts surge upward like freed anchors. The German pilots are stunned. Only months earlier, their FW-1908S and BF-109GS could dictate every engagement, diving, zooming, playing gravity's favored sons. Now, as the P-47s crest the bomber formation and continue to climb, it's the defenders who struggle. Their engines wheeze above 25,000 feet. Their boost pressure fades. Gabreski glances across his canopy edge. In perfect symmetry, a fellow Thunderbolt keeps pace in the rarefied blue, Lieutenant Robert S. Johnson, already notorious for bringing home a jug riddled with 21mm shell holes. Their machines, products of the same mechanical ingenuity, now perform far beyond the specifications printed months earlier in Republic's manuals. Then, at altitude, comes the turning point. Enemy fighters dive out of the sun. The Thunderbolts roll into counterclimbs. Normally, a defensive climb means suicide. Too slow, too steep. But now the turbines keep chanting, and manifold pressures stay green. The heavy American aircraft outclimb their pursuers, roll over, and dive back with terminal velocity. Gabreski's guns bark at 600 rounds per minute, 8 Browning .50s releasing a metallic roar that merges with the turbo's howl. A German FW-190 explodes in sparks, pieces tumbling past empty sky. Johnson follows through a quarter loop, firing at another. The fight lasts minutes. When the smoke clears, Allied gunners confirm 9 German losses, with 0 Thunderbolts lost at altitude. It isn't luck, it's physics finally tipping in their favor. Across the 8th Air Force, that day marks something palpable. The term climb rate parity disappears from pilot debriefs. The turbo, this once temperamental appendage of ducting and gauges, has become the beating heart of Allied air supremacy. In maintenance tents that night, word spreads informally. The tweak works. Mechanics exchange knowing smiles, trade notes, even etch tiny symbols under access panels, a tradition signifying which crews had hot turbos. It is superstition and pride rolled together. For months afterward, historians would cite this period, March to June 1944, as the P-47s' decisive emergence as an all-altitude dominator. Statistical curves in Air Force archives expose the pattern clearly. Mission completion rates for escort fighters climb. Bomber losses plummet. Luftwaffe engagement altitude drops steadily as the Germans retreat to lower, denser air where their engines still breathe. Elsewhere, high above the Ardennes, a group of 56th Fighter Group pilots perform a routine once physically impossible. They intercept a formation of BF-109GS attempting to dive on returning bombers near Liège. The Thunderbolts not only meet them, they pass them vertically, forcing the Germans into evasive dives that shatter formation discipline. Post-mission analysis calls it tactical inversion. The defenders no longer hold gravitational advantage. All of this unfolds because a few inches of mechanical travel in a linkage transformed how turbine pressure delivered power. Simple to describe, impossible to overstate. To observers on the ground, these engagements seem miraculous. To historians, they represent the synthesis of machine and improvisation finally fulfilling design potential. The Luftwaffe's intelligence branch takes notice. By spring 1944, decoded radio intercepts mention American fighters with high-altitude compressors of remarkable output. One exasperated German report concludes, they now own the upper air. For the men who maintained those compressors, triumph feels both vindicating and tragic. They know how fragile their work remains. A single missed grease bearing or a warped duct could undo everything. So they labor through sleepless, rain-soaked nights, adjusting valves, tightening bolts by lamplight, to keep perfection alive over clouded skies. From that March morning onward, whenever American pilots brief for missions, a quiet refrain passes through the ranks. Remember the turbo. It means, trust the men who built your climb. By mid-1944, that trust would be tested beyond imagination, when the same technology that made the Thunderbolt supreme would be pushed to its limit in combat so dense, even its massive turbine might choke on the smoke of war. June 6, 1944, Operation Overlord. Before dawn, the sky above the English Channel hums with metal and nerves. In hangars along the southern airfields, P-47 mechanics wipe their hands on rags that have long since turned black. Each jug has been checked thrice: boost calibration, turbo duct pressure, ignition sequence, fuel mixture. This is the morning everything has been leading to. At 0430, engines ignite one by one, a rolling thunder that gives the aircraft its unintentional nickname. There's no ceremony now, no grand speeches, only faith in the machinery. The newly refined turbo-supercharger systems will be asked to perform at full stress for hours on end, in the densest traffic the skies have ever seen. As the invasion fleet gathers below, Thunderbolts patrol in layers above the beaches, climbing and diving between bomber waves and transport gliders. German response is fierce. JG-2 Richthofen and JG-26 Schlagiter, elite Luftwaffe wings, scramble from northern France to intercept. For the first time, both sides throw nearly everything with wings into a single day. At lower altitudes, dogfights blur into chaos. Tracers crosshatch gray mist, searchlights pierce the smoke. But higher up, at 25 to 30,000 feet, where the thin air hides contrails and faint threads, the real technical test begins. There, the P-47s turbo reigns supreme. Luftwaffe formations struggle to climb efficiently from low bases near the invasion zone, their engines gasping as manifold pressure drops. The Americans, cruising above them, see it unfold like a slow-motion chess game. One observer later described it. They came up in waves that broke apart before they could reach us. The turbocharged jugs, some with subtly overtuned wastegates, could hover at those heights, pick targets, and then dive to attack with ballistic fury. Dive brakes aren't needed. The plane's mass carries it like a dropped hammer. Gabreski would later recall chasing an FW-190 nearly from the stratosphere to the deck. The faster I went, the stronger she pulled. It was the engine's roar that frightened the other fellow. Where earlier escorts might have broken away once fuel dwindled, the refined turbo systems allowed long-duration high-power settings without catastrophic overheating. Republic's engineers had quietly solved the earlier intercooler issue by rerouting duct flow, borrowing directly from field reports compiled in England. Mechanics saw their own innovations mirrored officially, a rare moral boost. That day, numbers tell the blunt truth. More than 1,700 P-47 sorties cover the beachheads, maintaining an iron canopy over Allied troops. Enemy air response falls to a fraction of expected levels. When Luftwaffe pilots describe their defeat later, they cite enemy altitude advantage. One veteran of JG-26 admitted, their strength was not numbers, but height. Always height, bought with monstrous engines. At the London Air Operations Board that evening, reports flood in. Allied command realizes that the war in the air has irreversibly turned. Climbing superiority, once the Luftwaffe's proud inheritance, has been repossessed by the Thunderbolt's turbines. Fighter command officers note how bomber formations complete the day's missions with minimal interference, something unimaginable a year earlier. Meanwhile, at an airstrip near Boxstead, mechanics greet returning aircraft. Some turbos glow faint red inside their housings from sustained heat. Yet most still function, not a single catastrophic rupture that day. A corporal stares into the cooling exhaust ports, shakes his head, and mutters, "She shouldn't live, but she does." From there, momentum feeds upon itself. Through summer 1944, the Thunderbolt becomes not just an escort, but an assault platform. With turbo-supercharged power, it dives to the deck carrying bombs and rockets, then climbs out before flak can catch it. Its engine, indifferent to altitude, turns the aircraft into whatever the mission demands. Bomber protector 1 hour, tank destroyer the next. The Luftwaffe, fracturing under continuous pressure, learns an awful pattern. Wherever Thunderbolts operate, their fighters cannot rise high enough to fight back effectively. By autumn, entire German sectors are advised to conserve fuel rather than pursue the invincible high fighters. For the Americans and their allies, the climb isn't just physical, it's psychological. Crews that once questioned their machine now swear by it. Young pilots boast they can fly over the moon if there's enough boost. The old anxiety about complex machinery dissolves into quiet devotion. The turbo, once the maintenance man's nightmare, has become the airman's salvation. General Dwight D. Eisenhower's after-action notes for Overlord include a brief acknowledgement of fighter performance exceeding expectation in both altitude and range. Behind that restrained phrase lies the unglamorous triumph of metallurgy, patience, and one innovative adjustment that liberated power no one had planned for. As summer fades, the European air war takes on a new complexion. Allied bombers strike deeper. Luftwaffe intercept units suffer attrition they cannot replace. In every chart pinned on intelligence walls, one common element appears next to every successful mission: P-47 escort available. The altitude lines now favor the stars and stripes. And from those hardened airstrips, half mud, half metal, mechanics continue their quiet rituals, tightening the same bolts, testing the same temperature gauges, ensuring humanity's strangest hybrid of brute force and ingenuity keeps breathing thin, cold victory. When the smoke of D-Day clears, the world will count victories and losses on paper, but those who were there will remember a sound: the eerie metallic wail of a turbo at full throttle, echoing through heaven's upper corridors. And from that sound, history descends into its next echo: consequences, myths, and a reckoning for what such power achieved and what it cost. When the summer skies of 1944 finally softened into pale blue August haze, the data told a quieter but far more decisive story than any headline. The Luftwaffe, once the unchallenged master of altitude, had been driven downward, both literally and strategically. Intercept transcripts collected after D-Day make the change clear. German controllers began instructing their pilots to avoid combat above 20,000 feet if possible. For an air force that once defined modern high-altitude warfare, such orders were unthinkable. But the physics of exhaustion had arrived. German piston engines, forced beyond their design ceilings, could no longer compete with the relentless American turbos singing overhead. The Thunderbolt's dominance now rippled across every front. In France, P-47s roamed in fighter-bomber sweeps, striking trains, convoys, and bridges, then looping effortlessly back into thin air to evade flak. Pilots used to joke that the Germans had to fight not just the enemy, but gravity itself. At altitude, the Luftwaffe found itself alien. The same turbo that gave the Jug its exceptional climb now gave it range and versatility. Because it maintained engine efficiency, the P-47 could operate at partial throttle even while carrying heavy bomb loads, conserving fuel and stretching every mission deeper into occupied territory. The once overcomplicated machine had become the logistical cornerstone of Allied air strategy. By late 1944, statistical analysts in the U.S. Army Air Force's headquarters at High Wycombe charted the transformation with clinical precision. Average bomber escort loss ratios fell from 10% in early 1943 to less than 2% by that autumn. German industrial centers like Schweinfurt and Regensburg, which had once seemed unreachable, were now struck repeatedly with minimal interception. To the men on the ground, the numbers meant survival. Bomber crews returned from missions talking less about fear and more about noise, the comforting growl of Thunderbolts materializing out of the high clouds. Mechanics in those English bases would grin when they heard that. Noise meant everything was working as it should. For the Luftwaffe, the same sound meant despair. Their high-altitude reconnaissance flights reported columns of vapor trails stacked above them like unseen stairways. The Jug looked slow and clumsy from a distance, but up close, it was a mountain falling from the sky. Even as the Germans introduced jet fighters like the Me-262, those came too late and in too few numbers to stem the tide. During the autumn offensive over the Rhineland, the P-47s turbo systems faced their final test: sustained power under freezing conditions and massive operational tempo. Over weeks of back-to-back flights, maintenance logs showed remarkably few catastrophic failures. Between April 1943 and December 1944, mechanical reliability of the turbocharger improved by nearly 50%, an extraordinary figure for equipment operating at the edge of physics. Every line in those maintenance charts whispered the same truth. Success did not come from perfection, but from iteration. The insane hack, born in a field tent, had been absorbed into formal doctrine, replicated across thousands of machines. What began as a mechanic's instinct was now standardized procedure, though few official manuals ever credited its unnamed inventors. On airfields from Normandy to the Ardennes, the rhythm of war changed. Thunderbolts thundered out each dawn in waves, roaring through the early mist. Each takeoff was a small statement. Technology, once seen as too complicated to succeed, had become dependable through nothing more exotic than hard use and shared knowledge. Those who had doubted the design now faced overwhelming evidence. An aircraft dismissed as too heavy, too unwieldy, and too intricate had carried the air war across the Channel and deep into the Reich. The paradox was almost poetic. The same bulk that seemed a flaw had allowed it to house the machinery that made it great. And when the guns finally began to fall silent, that paradox, complexity yielding simplicity, would follow the Thunderbolt into the peace that came after. Winter 1945 descended not as peace, but as exhaustion wearing a thin coat of hope. Across Europe, airfields once trembling with the roar of Thunderbolts grew quieter. Rows of P-47s sat half-sunk in mud and frost, their great radial engines wrapped against the cold. Each was a monument to engineering excess turned virtue, a relic of the altitude war that had finally ended. The statistics were stark. Out of more than 15,000 Thunderbolts produced, roughly two-thirds had flown in combat. They destroyed thousands of enemy aircraft and untold lines of trucks, railways, and tanks. But their deeper victory lay unseen, in the corridors of post-war aviation science. Those who studied the wreckage of war sought lessons that would shape the future. Engineers dissected captured jugs and realized that Republic's long duct system had unknowingly foreshadowed the jet age. Its tail-mounted supercharger installation was, in principle, a primitive turbojet, exhaust propelling a turbine, generating compression for thrust. Within a few years, that physics would define the next generation of flight entirely. The individuals behind the advance scattered into history. Alexander Kartveli returned to design post-war jet aircraft for Republic, including the F-84 Thunderjet, a direct descendant in both name and spirit. Sanford Moss, already in his twilight years, watched as the gas turbine principles he pioneered became standard in almost every aircraft engine on Earth. And the countless anonymous mechanics who had coaxed miracles out of their turbos slipped quietly back into civilian life. Automotive garages, small-town airfields, university machine shops, carrying with them the memory of how intuition once conquered cold mathematics. To them, every roar of a jet that followed carried a faint echo of the old P-47s howl. The machines themselves continued serving wherever conflict demanded resilience over grace. In the Pacific, P-47NS escorted bombers to Japan's doorstep, their turbos still hissing contentedly at 30,000 feet. In Latin America and post-war Europe, surplus models flew on into the early 50s, long after sleeker aircraft had taken their place. Mechanics still performed the same ritual checks: turbine clearance, wastegate actuator, intercooler ducts. The same grease, the same touch, the same reverent patience. For the Luftwaffe veterans who survived, the Thunderbolt remained both inspiration and punishment. Many admitted grudging respect for its design logic, a sledgehammer that could dance, as one German ace called it years later. Technical institutes in post-war Germany would study American turbocharger manufacturing methods as a case study in the advantage of industrial breadth over minimalist engineering. The lessons of scale and flexibility were bitter, but lasting. In Allied circles, however, there was celebration tempered by reflection. The Thunderbolt's success, though born of ingenuity, came at enormous human cost. Thousands of maintenance hours per sortie, endless logistics chains ferrying parts across oceans, countless ground crews sacrificing rest to keep turbos breathing life into engines that should have failed under strain. Their victory was stained with fatigue and loss, but it had forged an unbreakable standard for what combat engineering could achieve when it merged intuition with science. By 1945, leaflets circulated among returning airmen included a quiet acknowledgement. The Republic P-47 showed us that complexity need not be feared. only neglected. It became a quiet mantra in hangars and laboratories alike. And as the war drew to its exhausted close, the final reports from Europe concluded with a modest understatement that belied the machine's titanic impact. The turbo-supercharger installation has proven itself decisive in maintaining power and altitude performance. But on nights when the air was cold enough to remind one of those English winters, a veteran mechanic could still swear he heard the ghostly whistle of a turbine spinning somewhere beyond the clouds, a sound equal parts triumph and sorrow. When the roar finally faded into memory, its echoes invited one last question. What, beyond machines and victories, did this towering contraption of pipes and flame tell humanity about itself? History remembers the P-47 Thunderbolt as metal and horsepower, but beneath its aluminum hides a more human alloy: trial, error, and something like faith. A faith that persistence could polish raw machinery into grace. From the drawing boards of Long Island to the mud-churned airfields of East Anglia, its story traces the climb of human ingenuity itself. For every name engraved in technical documents, hundreds remain written only in oil stains and burnt fingertips. Mechanics who worked without sleep, engineers who revised blueprints between bomb alerts, pilots who learned to trust a noise few understood. Together, they prove that complexity is not the enemy of reliability. It's simply truth wearing a harder face. The Thunderbolt's insane turbo hack, that small rebellion of field judgment against official design, stands as proof that progress is rarely neat. It is messy, incremental, born in half-lit hangars where necessity erases hierarchy. That unrecorded mixture of science and stubbornness outclimbed ideology and, eventually, tyranny itself. In the calm after war, the turbine principle they perfected would leap from propellers to jets, from the commerce of survival to the commerce of travel. The roar that once announced destruction became the hum of airliners binding continents together. Every modern jetliner, every sleek engine slicing through the stratosphere, traces its lineage back to those grease-smudged mechanics who refused to accept that a heavy airplane couldn't soar. Today, a restored P-47 sits silent in museums, its tail still bulging slightly from the massive turbo within. Visitors read the data plates: speed, ceiling, armament. But what they are really looking at is a philosophy: build boldly, learn constantly, and listen to the hands that touch the machinery. Because somewhere in that balance, between the clean line of theory and the dirty fingerprints of practice, lies the secret that carried the Thunderbolt higher than anyone believed possible. And when we watch a modern jet rise into the cold blue dome, we are, in a way, witnessing that same improbable climb reenacted. The echo of one mechanic's impossible idea, still ascending.